Good morning. I'm starting my lecture in a second. First of all, before continuing further, I would like to address a question that I was asked, and I did not have a chance to communicate this question to you because I was busy with preparing the project, and I wanted to give this project, to assign this project as soon as possible, because some students said that they want to start it already. So in page 1816, I was asked by a student, I forgot to write this plus sign. And the fact that I forgot this plus sign made the student wonder what was happening. He did not understand what was happening. This is actually from the previous page, from 2 pages before, 1814. We had this determinant, and I calculated this determinant here, okay? So these three terms, product of these three terms is here. Then these two terms times 0 is 0. Then these two terms times this term is here. Then I'm calculating negative terms. This product is 0. Then these two terms multiplied by each other, and this term with minus sign, and these two terms multiplied by each other, and by this one, minus sign. And then, please look, here I have sine KL over 2, sine KL over 2, and here I have sine KL over 2. Here I don't have sine KL over 2. But then I have sine KL. I say, sine 2 KL, sine KL equals 2 times sine KL over 2 times cosine KL over 2. I substitute this here, and then I have sine KL over 2 in each term. So therefore, I can take it out. Okay? Sorry for missing this plus sign. Pay attention. What happens is that because I wrote this page, so when I looked first time when student asked, I did not see this. That was natural to me that there is a plus there, nothing else. So I even did not pay attention that plus was missing. But, okay, student did not tell me that plus is missing. He said that maybe there are some problems with signs. Anyways, this sign was missing. Okay, now we will move to the following topic. So today is lecture 19. And that is as follows. We are nearing completion of topic of stability. Which is lack of buckling. And buckling. First topic that we studied was deflections. Question: any connection between these two topics? Answer is yes. Deep connection. Okay? I will start. In topic of deflections, of beam deflections, we evaluated function of displacements. V of x. In buckling, so we had differential equations. That is EI d2v dx square equals mz of x, or EI d4v dx in first power equals w of x. So that is bending moment. That is a distributed load. Here in buckling, we also are looking for displacements. Our differential equation is EI d2v dx squared plus PV equals 0. Okay, or that is for simply supported column. Or EI d4v dx in first power plus P d2v dx squared equals 0. Then in deflections, in deflection chapter, we just wanted function v of x. Here we want, here in buckling, we want to find for which value of values of P critical, so that is simply supported, for example. V of x is not identically 0. And then we want to find, of course, value of P critical equals which value. Now connection. Okay, in both cases, in both chapters, we had to deal with differential equations, ordinary differential equations. So engineers desperately need differential equations. Okay? Mechanical, civil, ocean, aerospace, automotive, engineering fields, need ordinary differential equations. Again, the following question arises. Question. Perhaps there is even more close connection between deflection chapter and buckling chapter. So specifically, let us, okay, I will be more specific with my question. In deflection chapter, we dealt with this beam. W0, the beam length is L. Then this beam deflects. And here there is this V maximum. Equals 5, W0, L in force power, 384 EI. So that is in deflection chapter. In buckling chapter, we studied for simply supported beam like this. P critical, and during this P critical, then this W is not zero, V is not zero. So V is like this. Okay? So in this case, V equals some constant, C times sine n pi x over L. C is not zero, n is a positive integer. I'm going up for some reason. Positive integer. 1, 2, 3, etc. And P critical equals n pi square EI over L square. Okay, smallest buckling load P critical Euler equals just when n equals 0. N equals 1. Pi square EI over L square. So these are two things that we learned. Connection. Now we will connect these things. Question, what happens in the problem when there is both transversely distributed load, W0, and axial compression P? I wanted actually to wait for you to give this response, but you are not here. I'm sure that in your room, in your office, in the place where you are listening to the lecture, you had this inquiry. Okay. Then we have to write expression. Again, we have this differential equations. That is EI V double prime equals moment. Okay? This equals bending moment. Okay. This load gives me actually this contribution minus P times V. These ones have reaction will be W0 times L divided by 2. That will be a reaction. Will be W0 L over 2 times X. Okay, maybe I will write it down here from next page. Again, I'm repeating, you of course know this by heart, by mind. So then this is a reaction. That is a symmetric problem. So that is entire load, W0 times L divided by 2. Then if I'm calculating here, then I'm having, look please. So that is a cut. We are doing cuts. That is MZ. So then that is 0.0. Sum of the moments of Z with respect to axis Z that passes through 0.0 equals 0. Okay? And there is load. W0L over 2. So will be minus W0L over 2 times X. This distance is X. Then here this load equals plus W0L over 2. Sorry, that is a load. Sorry. Here is W0 times X. That is a load. Okay, in positive direction. And arm is X over 2. And plus MZ. So then MZ equals W0L over 2 times X minus W0X squared over 2. Okay, so that is this expression. So I wrote it here. W0L over 2x minus W0x squared over 2 plus, minus PV. Because V is an unknown function. That is something we are looking for. Then I have to put it on the left-hand side, together with other terms that contain unknown function V. So EI V double prime plus PV. That equals W0L over 2x minus W0x squared over 2. Okay, we do it usually. We don't like to have one constant EIs and another P. I divide both sides by EI. So I get EI is gone. Will be V double prime plus P over EI V equals 1 over EI, W0L over 2x, minus W0x squared over 2. Now we denote, as we always denote, P divided by EI equals K squared. So we get actually this is inhomogeneous because there is right-hand side. Then ordinary differential equation. Ordinary because this derivative is with respect to x only. There is no derivative with respect to any other coordinate. Because that is inhomogeneous, then we need to find solution of complementary solution plus particular solution. Complementary solution is a solution of this part only, v double prime plus k square v equals 0. And particular is any solution of this equation. Any questions? Look, please. I may occasionally, suddenly, lose some sign plus or minus, but please check and tell me, and I will check material again if there is such a thing happening. At least this semester it happened only once. And that homework number 18 I solved because of request of students. So I prepared these several pages of presentation in order to explain to you how to solve this type of problems. Okay, then now we are talking about homogeneous problem. So homogeneous solution we already know. That is in lecture 13. We dealt with this when we had only this part, no, just buckling. V of x equals C1 sine kx plus C2 cosine kx plus V particular. Okay, now V particular, I say because this is a polynomial of second degree, there is x squared. So it makes sense to look for particular also in the same form. Alpha plus beta x plus gamma x squared. Polynomial of order, you see I misspoke here, of order 2 as the right-hand side. Alpha, beta, and gamma must be determined. Okay, let us calculate first that I have to substitute this V particular into differential equation to check whether it satisfies or not. So first derivative of this, first derivative of alpha is 0. First derivative of beta x is just beta. First derivative of gamma x squared will be 2 gamma x. Second derivative is 2 gamma. So I'm substituting now into this particular solution. So V particular double dot plus k squared V particular equals W0 EI Lx minus x squared. So second derivative equals 2 gamma plus k squared. Here I should write V particular alpha plus beta x plus gamma x squared equals W0 2i EI Lx minus x squared. So now I just substitute and rearrange the terms. So that is 2 gamma plus k squared times alpha. That is a constant. These are constants. There is no x. No x here. Then there is this term, k squared beta x. Then there is this term, k squared gamma, x squared. So this equals this term, W0 2EI Lx minus x squared. Now this left-hand side should equal to the right-hand side. Then this term must be 0 because there is no x here. And in order for this expression to be 0, then this term must be 0. 2 gamma plus k square alpha equals 0. From here, that is one thing. Second, that is first equation. Second equation, k square beta, that is this term, must equal this term. That is this second. Equals W0L 2EI. Coefficient in front of x must be 0. So from second equation, I get beta. Beta equals W0L 2EI k squared. I'm continuing, and I'm waiting here for a minute. So then third equation. Third. K square gamma, that is x squared. K square gamma equals minus W0 over 2EI. From here we get gamma. Gamma equals minus W0 2EI k squared. Now we have also this first equation. 2 gamma plus k square alpha equals 0. From here I get alpha. Alpha equals minus 2 gamma divided by k squared. Now 2 gamma, gamma we found. That is this one. 2 and 2 cancel each other. 2W0, 2EI k squared. And then divided by k squared. So 2 and 2 are canceling each other. We get W0, EI, k in fourth power. That is equation 5. So that is an equation then, V particular. W0 over EI, k in fourth power. That is this term alpha. Plus beta, W0L, 2EI k squared, that is x, beta times x. And then gamma minus W0, 2EI k squared, x squared. I will wait so that you could write down. And you will get all these pages. I will copy. Mr. Silva was kind enough when we had regular lectures to copy them after the lecture and put immediately on the web. Now I'm doing that. So that is this V particular. Now V, that is complementary solution plus particular solution. Okay, I just took out from here this W0 EIK squared appears everywhere. So this I took this coefficient everywhere. Then here will be 2 over k squared. Then plus Lx. That is this here. And minus x squared. Okay, once I have this, I have to satisfy now boundary conditions. So V at 0 equals 0. Then C1 times 0 is 0, so this term does not appear in this equation. Plus C2 times 1 plus W, then x equals 0. This is 0, this is 0. 2 over 2 is 1. We get W 0, EIK in fourth power. So C2 equals minus W 0, EIK in fourth power. Now V of L equals 0. That is first boundary condition, and that is the second boundary condition. V at L, so then I substitute here. C1 sine KL minus then C2 we found. C2 is minus W0 EIK in fourth power, cosine KL, plus W0 2 EIK squared, 2 over K squared, L squared minus L squared. But L squared minus L squared is 0. This is 0. So then pay attention, these 2 and 2 will cancel each other. I will get EIK in fourth power like here. So coefficients will be the same, W0 EIK in fourth power. But here there is plus sign, here is minus sign. So I can take out this and we'll get 1 minus cosine KL. So that is 19.6. So then we will get 19.7. So from here we can get C1. C1 equals, look please, this transfer, W0 EI in case for power cosine KL divided by sine KL, minus, this 2 and 2 cancel each other, W0 EI in case for power divided by sine KL. So V of x equals then W0 EI K in fourth power, then cosine KL divided by sine KL, minus, then I took this out, this is taken out here, 1 over sine KL. And this is C1 is multiplied by sine KX. Okay, C1 sine KX. This comes from there. Then, with cosine, that is C2, W0 EIK in first power cosine KX, plus particular solution. And look, I forgot here this. Look, I'm doing derivations at home. I'm preparing lectures at home. So then I can rewrite in a more compact form. W0 EI K in fourth power. Then look, sine KL can be taken out. Minus can be taken out. Will be 1 minus cosine KL. Sine KX over sine KL. Then these 2 and 2 are canceling each other. I will get K in fourth power. Then I took this term out. So it will be 1 minus cosine Kx. This 1 from here, 1 minus cosine Kx. Plus then terms from here. This is taken out. So here, however, there is k squared. So, but here I took out k in fourth power. So therefore, Here we have k squared over 2lx minus x squared. So that is a solution that is both complementary plus, this is v equals v complementary plus v particular. That is everything. So that is this displacement. Now, 17.8, just one question 19.8. So that is this column. Column is simply supported. There is this load, axial load P. Now, what is the role of this distributed load? What does this W0 distributed load represent? Where is it coming from? Just our curiosity? Okay, this could be possible wind loading. You see, if you do not consider it, then you did not design for possible wind loading. Or so there is this airplane's wing, then that is sudden turbulence. Okay? So when designing against buckling, what does that mean? P must be smaller than P critical. We also have to think on possible perturbations from ideal state, ideal situation. Okay? So we encounter real life situation. Okay, when there is such a load, what happens then? It is not that I asked, oh, we studied deflection separately, and we studied buckling load separately. Now, maybe we have a curiosity, what happens when these are together? Yes, that is a question that might come from curiosity. But we do not deal with this just because of curiosity. We deal because there could be possible wind load or possible disturbance. Or, for example, you were running. Imagine that this is structure. But you are running and you suddenly give a kick to this structure. We don't want it to collapse. Okay, we are continuing. So both W0 and P together represent realistic situation. I will get more pages from my binder. So, 19.9. We discussed until now, we did not finish this until now, two realistic perturbations of ideally centrally loaded column. Okay, one thing is, look please, ideal is like this, that is a column, I'm just depicting beginning. Then that is a centroid, and load is like this. That is ideal situation, and that is centroid. Second, okay, that is ideal. Now, non-ideal. So that is centroid. But load is applied here. So this is eccentricity E. And second is like this. Even if the load is applied in the center, that is centroid. Then there is possibility of such a load. Okay, so these are both non-ideal. Realistic situations. If you pay attention, I'm providing ample discussion of what we are doing, because if we go just by the book, then it will be not possible to detect these book authors. I will write down not only this book, but book authors do not pose, as it were, to answer the following question. What are we doing now? Why are we doing what we are doing? Okay, we discussed this case and this case. So you see also connection between these two parts that we did. That is ideal. That was not known until 1744. So let us find, so we found the displacement. Let us find the bending moment, 1910. Why do we want bending moment? Because from bending moment, I can calculate sigma, bending moment divided by moment of inertia times c. Okay, just I will make like this, 1911. We need not only V of x, displacement, and to design for stiffness, but also bending moment, mz of x, bending moment, to design for strengths. Okay, sigma equals mz divided by I times c. So, for example, if it is a rectangular cross-section, then that is centroidal axis. Then this is C. C. That is extreme fibers. Where maximum sigma occurs. Or sigma equals m divided by section modulus. Section modulus equals I over C. In German textbooks, this equation is written just beautifully. Sigma equals m divided by w. So their section modulus, w is section modulus, but they call it Widerstands moment. That is moment of resistance. Why do I call it beautiful? Because this formula is called mirror formula. Okay, moment and W, they are like mirrored with respect to this dashed line. Okay, that is very useful for remembering this formula. So then what you have to remember is moment divided by W. Then instead of W, in American or Anglo-Saxon textbooks, it appears as section modulus, and it is not called moment of resistance. Resistance in German is Widerstand. Okay, therefore they denote it as W. Okay. So, next page, I say. So then I just differentiate 2 times. I get W0 over K squared, 1 minus cosine KL, sine KX. Look, please, here I have it. Then plus cosine KX minus 1. Where is the biggest bending moment? At L over 2. So M maximum then will be W0 K squared. So then will be sine K L over 2. But sine K L over 2 can be divided. So we just do some algebra. And we get cosine KL over 2. 1 minus cosine KL over 2 divided by cosine KL over 2. So when K is small, we get W0 L squared 8, like in this problem. okay? Because here in the, that equals W0L over 2, that is a reaction, times L over 2, then minus W0X squared, that is 2. L over 2 squared will give me this formula. So this is what we remember. I hope you remember this formula from strengths of materials, from previous course. Everything, static strengths and these intermediate strengths of materials are interconnected with each other. And we need to know strengths in order to know intermediate strengths. Now, when P goes to P critical, that is pi square EI over L square, what happens with this K? Look, please. Instead of K, we will have, okay, what is cosine? So then instead of K equals P critical over EI times L over 2. Instead of P critical is pi square EI over L square, and then EI. EI and EI cancel each other. So we get cosine pi over 2. Cosine pi over 2 is 0. So that means that when buckling load is approached, then maximum displacement goes to infinity. And bending moment bending moment also goes to infinity. Any questions? Please, please, please communicate to me the questions. So everything is, I would say, extremely beautiful theory. Everything fits very beautifully. We get limiting cases that we studied in strengths. In statics, it's important to know what is centroid, where is the centroid. Notion of moment of inertia is important. Here, buckling, and main thing is that realistic situation is different from ideal situation. Yes, we are using safety factors also. So idea of safety factor is also because of realistic situation. I will continue this topic. So 1911 we covered, 1912. I'm dealing with this topic now, specifically now, because yesterday I assigned you the project, and this topic is problem number 2. Pay attention. In the project, I deliberately limited myself with 2 problems only. They need use of differential equations, solutions, they demand knowledge of strength, so you will have to review whatever you need in strengths. Now you may say, okay, this distributed load was acting as a wind, but maybe wind is approaching only in short place, not for the whole beam. Maybe there is some wind flow only, or gas flow here. Okay, then situation is like this. P and P. Here is a load N. Why I noted N? N, normal load. So this is now, actually it's called beam column. Why beam? Because transverse loading is here. Beam usually works on transverse loading. Column, but there is axial compression. Okay, when we had only axial compression, the moment was written as EIV double prime. And this moment was minus PV. Now we have a different situation. We have P and also N. So we will have to write down expression for the moment differently than this. Any questions? No. When I say no, actually, I mean, you are not sitting here, you and I both are prevailing over coronavirus. Why? Because we are continuing to teach, you are continuing to study. So we are succeeding in fighting coronavirus. It seems to me, in my humble opinion. And America and entire world will prevail over coronavirus. But we have to keep social distancing. But it does not mean that we are distancing ourselves from each other. We are in electronic contact. There is technology that connects us. Please use that technology to contact me if you have any question, even slightest. Okay, now I will write down this 1913. So bending moment then equals, look, if load is in the middle, then reactions will be n over 2. So n over 2 times x minus PV. So that is for the first part. And I assume that this load is in the middle. Because I assume this load is in the middle, there is a symmetry of the displacement function with respect to mid cross-section. We can consider only that the half beam. Now, if the load is not acting in the middle, then we have more work to do. We just have to integrate differential equation on the left side to the load, right side to the load, then Taylor solution under the load. We will consider simpler case, but even this simpler case is quite long. Due to symmetry of displacement function with respect to mid cross-section, we can consider only the half beam. So, EI d2v dx square equals mz. mz equals n over 2x minus pv. So I'm writing down EI v double prime, I just rewrote this, plus pv, because I transfer this unknown function to the left side to have unknowns together and knowns together. I divide again by EI. I get v double prime plus p over EI, v equals n over 2EIx. That is k squared. I denote again as that is our notation. So with a high k squared, we remember you. So then I write v double prime plus k squared v equals n over 2EIx. That is ordinary differential equation with constant coefficients and inhomogeneous. Why it is inhomogeneous? Because there is a side load. There is a transverse load. This gives rise to inhomogeneity. If there is something, or moment, or something else, then this will be, and I assigned you in the projects, okay, 1914. In the project, I assigned you, for example, problems like this. Moment here, M0, M0 and M0, or some other loads. Okay, 1915. V equals V complementary plus V particular. Now this is complementary is the same. C1 sine kx plus C2 cosine kx with V particular. Because on the right-hand side I have linear function, so I'm also looking particular as a linear function. So AX. Previously I denoted as beta x. If you want, I can denote it also beta x. So I substitute then beta x double prime is 0. This is beta x, that equals So from here I get beta k squared x equals n 2ei x, so beta equals this. So particular solution is n 2ei k squared x. Now what is eik squared? Eik squared is ei, then n divided n, okay, ei times p, sorry. P divided by ei. So ei and ei cancel each other, we get p. So v particular then equals n, this guy equals 2px. That is particular. 1916. V equals V complementary plus V particular. C1 sine kx plus C2 cosine kx plus n 2p x. Boundary conditions. Okay, 1. X equals 0, V is 0. So C1 sine 0 plus C2 cosine 0 plus this 0. So this is 0, this is 1, C2 is 0. So what is left then is C2 is gone. So C1 kx plus n over 2px. Now we study Hauser beam because of symmetry. Okay, so that is the alpha beam that we studied. So here, because of symmetry, that will be maximum displacement here. So V prime must be 0. X equals L over 2, V prime is 0. Symmetry condition. So V prime equals from sine k1 cosine kx plus n2p, that is first derivative, equals 0. So C1 equals minus n 2pk cosine kl over 2. So V of x equals minus n sine kx. That is, this is multiplied by sine kx. Then particular n over 2px. Or I can just take out this and write it down. And 2pk cosine kl I take out. Will be here minus sine x. Here will be kx cosine kl over 2 because cosine kl and cosine kl can cancel each other. And bending moment, y, again to calculate stress. mz equals ei v double prime. So second derivative. Second derivative will be ei. Second derivative will be giving me k squared. But eik is this n, 2pk cosine kl, sine kx. This is the first derivative will be constant, and then second derivative will be 0 from here. Second derivative of minus sine kx is plus k squared sine kx. So this guy equals p. P and p will cancel. So will be then 2k cosine kl over 2 sine n sine kx. So V maximum equals V over L over 2 equals, I just substitute here L over 2. Then will be KL over 2 cosine KL over 2 minus sine KL over 2. And then this cosine KL over 2. So I can divide cosine KL over 2 and cosine KL over 2. I will get here just KL over 2. and cosine will cancel each other. Sine over cosine is tangents. You see, we need also trigonometry, otherwise, without it, we cannot get anywhere. So that is a V maximum. That's the maximum displacement. M maximum, that is, okay, here, sine KL over 2 divided by cosine KL over 2 will be tangents KL over 2. So 1918. So that is this expression. Okay, now we can do observations. Vmax is directly proportional to the transverse loading N. That is here. Here, Vmax. Vmax is not directly proportional to P. Why? Because there is K here, and K contains P's, and tangents, K contains P. Depends through K. What happens when P goes to critical value? P critical equals pi square EI over L square. Your anticipation? What is your anticipation? You are not here, but I'm still asking you this question because I would like you to ponder at home about this. By the way, sorry for this deviation for 1 minute. The best recommendation I can give to every student now is not to work at all last month. I very much hope that we will go over this pandemic, and then everything will be open, all businesses will be open, we can again start to work full time. Now best time is to devote to the education. So your anticipation. Okay, if you anticipate that displacement will go to infinity, you are right. That is what we had in previous problem. Vmax is proportional to 1 over cosine KL over 2. So where does Vmax goes to? When cosine KL over 2 goes to cosine P over EI, L over 2. But instead of P, I write pi square EI over L square. And then EI. EI and EI cancel each other. From L square, I get L. L divided by L will be 1. So then we get 1919. Cosine pi over 2, that goes to 0. That means that Vmax goes to infinity, Mz goes to infinity. Wow, I think that is a stunning result. Both results are stunning. I knew that such results should have been obtained. That kept me from making mistakes in the road. Why infinity? Why displacement goes to infinity? Okay, this is we used for MZ approximate expression. That is this one, MZ equals EI V double prime. But more exact will be V double prime 1 plus V prime cubed, and then 3 halves the power. That is exact solution, exact expression. So then, if we are using this more difficult and nonlinear differential equation, then we don't get this infinity. But still, displacement is very high. Okay? So with this, I will write down no infinite solutions, but still Vmax and Mz max very big. Science is approximation. That maybe is a bit surprising fact, but science is approximation. Without approximations, we cannot get anywhere. Pay attention. First, we started centrally loaded beam and obtained solutions. Then we said, oh, but there is a transverse load. Let us remember this. That means that centrally loaded beam is an approximation of reality. Everything that we do in science is approximation. That is a damn good approximation. But it is approximation. Until we know something, we don't know it. Until Euler found buckling load, we did not know how to calculate against buckling. People did know buckling. People knew buckling 2,000 years ago. Ptolemy, for example, Vitruvius in Rome, 2,000 years ago, know it, but they did not know how to calculate the structures. Any questions? (1920). So we will discuss one more question just. What happens if axial load is zero? Are we getting expression we had in the beginning of the course, in the section deflection of beams for this beam? Okay, for this beam, if you remember, that is how we solved. EIV double prime equals n over 2 times x for half a beam, because there is a symmetry, so we consider half a beam. Because of symmetry. So EIV double prime equals n over 2x. EIV prime equals n over 2x squared over 2 plus C1. That's first integral. One more integral, EIV n over 2x cubed over 6 plus C1x plus C2. Boundary conditions, V at 0 equals 0. V at 0 equals 0. So we get 0 plus 0, C2 must be 0. (1921). So in the middle, we demand V prime to be 0 at x equals L over 2. So we will have n over, okay, V prime, n over 2 times 2 is 4. Okay, 2 times 2 is 4. So n over 4, L over 2 squared plus C1 equals 0. C1 equals, then this L squared over 4, 4 times 4 is 16, minus n L squared over 16. So the equation becomes like this, EIV equals nx cubed over 12 minus nl squared over 16x. How much is the displacement in the middle? X equals L over 2. We put L over 2 cubed minus then L over 2. That is 2 cubed is 8, 12 times 8 is 96, 16 times 2 is 32. So common denominator 96. 1 minus 3. So it will be minus 2 times 2 over 96, or minus 1 over 48. So we are getting minus 1 over 48 NL cube over EI. So that is a displacement that we got in deflection part. We got in deflection part. Are we getting this expression when P goes to 0? Okay, in our new setting? Question. And what is our new setting? That is this. That is P, and that is this N. So when this goes to 0, are we getting this from what we did? Answer is yes, we get this. We had the tangent KL over 2. So tangent KL over 2, asymptotic expansion, is like this, Taylor expansion. So then we have KL minus tangent KL over 2 equals then this term. 2 cubed is 8, 8 times 3 is 24. So V max then equals this.